All right, thanks for having me here. Today I'm going to present about nanoscale functional imaging of emerging photovoltaic materials. So I guess not many. Nice. So can everyone hear me well in online? Is it?
Yeah, we can hear you.
Okay, that's great. So yes, I will be sharing some of my recent works on functional imaging, especially on photovoltaic materials. Before I, okay, let me see. Okay. All right, it's like this. Okay. All right. Before I go into functional imaging of photovoltaic materials, I'd like to give a very brief overview of the solar energy and PV market, which isn't going to be long, but just wanted to take up a little bit of introduction to where we are up to and where we are heading to. So if you take a look at this history of photovoltaic cost and price reduction, so there has been a very sort of dramatic cost reduction in past few decades. This is showing the cost and prices of PV module reported from different literatures, and you can see that there has been a like 7% year reduction from 1975 to 2015. But recently, the cost of PV has dropped quite dramatically. Now it's heading over less than 20 cents per watt, which, if we calculate again, that's going to be another like 20% per year reduction per year. So that's very interesting and substantial decrease in terms of PV cost. And recently, the International Renewable Agency says that now the PV is the cheapest sources of the electricity in most countries, and obviously now offers some of the lowest cost electricity ever seen. So we are seeing a huge changes in terms of electrical costs in PV, including PV and other resource renewable energies as well. So we have currently up to around 760 gigawatts installed, and you can see that the new installation is also increasing quite a lot. And if you can imagine that the 1 gigawatt is around a sizable coal or a nuclear power plant, so it's a quite sizable power station. And the industry is now expecting to grow 1 terawatt per year by 2030. So that's also quite substantial increase. Oh, okay, so that's what it is. Okay, now I have a like animation going on. So it's yeah. Sorry. Is it okay? Okay. And another sort of challenges we face is that, so if we are going to install, if we are going to have like a terawatt capacity per year, we might face different challenges like other metallic, such as aluminium. So those metals used for frames and electrodes are going to be another challenges in this terawatt level of capacity. So, but we are definitely heading there, and we will see some nice impact of such terawatt installation. So this is a very recent report from Climate Change 2022, which has just reported in 4th of April this year. And they found that the solar energy is most has the most potential contribution to net emission reduction of CO2. So you can see that around 4 or 5 gigaton per year can be reduced per year if we use solar energy. And so having such a terawatt level of capacity in PV is quite has a huge impact on CO2 emission and global warming. This is a graph from Global Carbon Project reported in 2014, and this is a graph showing that the CO2 emissions that we need to reduce in order to keep the global warming below 2 degrees Celsius. And if we have, if we can reduce around 4 or 5 gigatons of CO2 every year by having terawatt level of PV, we can obviously have a huge impact on global warming as well. So we can see that the PV is now playing a very important and major role, not only in reducing the cost of electricity, but also on CO2 emission. That was sort of a brief summary of where we are in terms of solar energy. So the cost of PV is now the cheapest energy in many countries, and we are expecting to have a terawatt level of PV capacity by 2030. So here I'm going to briefly talk about overview of PV market. As you can see from this image here, we have thin film and monocrystalline silicon and polycrystalline silicon. So you will often see on the roof or commercial PV installation area, you can see these two types of PV panels most often. So thin films are rarely installed. I don't think we can see these panels, thin film panels, often in like nearby areas. It's only installed in very early stage of the development, but it's no more produced a lot. So you can imagine that these two are the most common PV panels, and this is obviously can be reflected in the PV market dominance, where you can see that thin film, you can see that blue area, it's only like 20%. You can see that it's been even reduced compared to 2013. So majority of the PV panels are from wafer-based silicon solar cells. And you can see that the multi-crystalline silicon, which is the dark blue, they are also decreasing, whereas the red, the crystalline silicon ones are progressively increasing. So we will, in 2020, I think we have more than 80% of single crystalline monocrystalline silicon panels. So thin films are not that impactful in PV market at this stage. However, many people are expecting to see a usefulness of the thin film, especially for tandem solar cells, which uses a silicon cell as a bottom cell, and we are going to deposit a thin film, wide bandgap thin film solar cells. So if you can see this graph here, you can see that bottom solar cells made of silicon can cover the wavelengths from IR range, and this has been most effective range for silicon solar cells to produce power. And the top cells are in the visible range, and you can effectively produce electricity from around 300 to 700 nanometer of the wavelength spectrum. So theoretically, silicon cell itself can have an efficiency around 26.7. That's record efficiency. And theoretically, they cannot have around 29 to 33% efficiency. Whereas if we have a top cell stacked on top, we can push that to more than 33%, and theoretically up to 45%. So the current record of the tandem cell is around 30%. The biggest difference between wafer-based silicon, which is now turning into mostly single crystalline, and I guess you guys are probably aware of what polycrystalline is, but thin films are mostly polycrystalline, except for the ones that have been done the single crystal transfer of the thin film. When you grow thin film onto a glass substrate or any type of substrate, they are usually polycrystalline. So as you can see, polycrystalline, you have crystals with different orientations, and that means we have a grains with different orientation and grain boundaries. And in many electronic materials, grain boundaries are found to be a defective area for that promotes non-radiative recombination. And what we mean by non-radiative recombination is that we have a trap level exists in between the band gap, and when excess carriers are generated, they get trapped and recombine in that energy level. So we sort of waste our carriers rather than having a valence to conduction band to band generation. So that's found to be very harmful in terms of electronic properties. So that's why people, especially in silicon, people try to move on to monocrystalline silicon. So yeah, as I explained, the grain boundaries are sort of very defective area where we have many different types of defects. You get some amorphous regions, so it's non-crystalline in that area, which generates many trap states, as well as you can see that there are broken bonds and some like anti-sites defects as well. And all these trap sites, as you can see, creates trap states in the band gap, and also attracts majority carrier to exist at the grain boundary. Therefore, you have such a band fluctuation going on with our trap states. So that's a quite common expression of the grain boundary in terms of electronic properties. However, okay, this is blocked, but let me see what I can do. Okay, I might need to, I might need to explain this. This is a data I've collected for silicon and different types of emerging thin film technologies, obviously polycrystalline thin film technologies. The best efficiencies compared to, I compared with the type in single crystal and polycrystalline. For instance, in silicon, you have better performance in when it is in single crystalline. However, in other types of materials such as carbon telluride, SiCs, cassiterite, and perovskites, they can be also made into a single crystal. You can make a single crystal like pellets, and you can even make a sizable material using, for instance, in perovskites. However, we see that perovskites and other materials have their efficiency, actually polycrystalline efficiency surpasses the single crystalline, which means that the grain boundary probably shouldn't be interpreted the same way as the silicon did. And also all these small defects such as grain boundaries, and there are many more defects in polycrystalline material, they need to be carefully understood for further efficiency enhancement. So this is sort of giving you an idea why we need to study nanoscale defects in this kind of materials. So yeah, this was a brief introduction to current PV market and where we are heading in terms of thin film technologies. So I'm going to be, because of that reason, I have been working on nanoscale functional imaging, which can probe individual defects in nanoscales. So I usually use atomic force microscopy for this purpose. And you can see that atomic force microscope was first introduced, the concept, and I think the first demonstration was first introduced in 1986 from Stanford and IBM. And they have explained that if you use a very small nanoscale tip and you have a sample, we can make them to interact in terms of front atoms. So the very bottom atom of the tip, which can interact with your sample directly, then you can translate that into imaging, and that can have a very high resolution without disrupting the sample. So the resolution can be more than 10,000 times better than the optical diffraction limit. And so it's obviously a touching, so mechanical forces translate into imaging in atomic force microscope. So we can do many things, like we can add many functions in atomic force microscope. You can have Kelvin pro force microscopy, and you can also have a conductive AFM. So these two are the main microscopy techniques that I employ in PV materials. And you can see in Kelvin pro force microscopy, we can have a work function. You can also see a charge carrier generation and separation. Using that, you can also profile PN junctions, and you can also image the ion migration, which I will show you later in my presentation. So in Kelvin pro force microscopy, you don't contact your sample directly to your tip, to the sample. So they have a like 5 to 10 nanometer distance in between the sample and the tip. Whereas in conductive AFM, you have to make a contact to the sample, and you can obviously map the conductivity. And if you use a external laser source or light source, you can also have a charge carrier collection mapping, so water current mapping, and you can also have a local IV curve using this AFM mode. So these two are main techniques that I employ. And one of example I'm going to show you here is that the Kelvin pro force microscopy, which you actually see differences in differences between work function between the sample and the tip. So you can see from this diagram here. Let's see. So you have a certain work function of tip and a certain work function of the sample, and the difference is called contact potential difference, which you can map in nanoscale. So that's a CGTS thin film topography. You can see many grains with different sizes, many different features, and this is the CPD mapping of this topography. Actually, they can be obtained in the simultaneously, so you can map topography and CPD imaging at the same spot at the same time. And so this is before having passivation of this CGTS thin film, and this is after you passivate your sample. So the topography hasn't changed, but the electrical property has changed, which means that you can see a huge difference between these two images, where you don't see any more like clear grain boundaries in CPD image. And that's a sort of a big advantage of doing this mapping, where you can actually get an electronic information whether your topography has changed or not. You can map this in different ways. So it should give you a very good information how your surface electronic property has changed. So this is a good example of the KPFM measurements. So today I'm going to specifically talk about halide perovskite materials, which I have been working in past 7 years on using this instrument. I guess many of you are probably familiar with halide perovskites. So they have A side here, which is usually organic cations, methylammonium, formamidiniums. So those A side are sitting in here, and you have halide and lead side in the middle here. And halides, we often use iodine or bromides, and leads, the lead is the most common metals, and where people now trying to use non-toxic material to replace lead with a tin, but still the highest efficiency and highest performing material is lead-based perovskite materials. So you can have multiple composition. You can have methyl ammonium lead iodide and bromide. You can mix the halides into different ratios. You can even mix the A sites. You can have both formamidinium and methylammonium. So you can by doing that, we can tune the band gap, especially when we put more bromides. If you increase the bromide portion, you can enlarge your band gap. So you can see that. So that's 100% iodide, X equals 0, and you can gradually increase your band gap by putting more and more of the bromide. So if you have around, so that's a calculation showing that if you have around 0.4% of the bromide, so 40% of bromide, you can have a band gap around 1.7, and that's sort of an ideal band gap for the tandem silicon-based tandem solar cells. So in halide perovskite, we can tune the band gap by having different ratio of the halides. However, there comes a problem, stability problem, where if you mix them too much, say, if you have like 10% of bromide, the material is stable. However, if you increase bromide at above certain level, say more than 20%, you're starting to have instability issue called phase segregation. So what you mean by phase segregation is that in dark, they are nicely distributed. So you have a certain band gap in one material, which is quite obvious. But once the light comes in, so when you shine light, you're starting to see a segregation of different halides. So you have here you can see the iodine has been sort of accumulated in certain area. You have some bromides. So you in the same material, you tended to have a band gap, different band gaps. So bromide band gaps is usually higher, and iodine band gap is smaller.